Okay. So this week we still continues the talk about the importances of the hydrogeological system in the applied geology studies. There will be different discipline issues. And next week, the way we'll have these classes to provide a lecture about the soil classification and also some of the soil mechanics content. So you will be able to understand some of the how to classify the materials and then how to using the concept. Like you might also go to the lab to take a look at the core sample and then to understand the laboratory test. Okay, and after that we can have the concept what's the really geology that you might meet or hydrogeology you might meet, and use that to doing the hydrogeological models constructions. Okay, and in this project, in these classes, I'm thinking that the final originally we mentioned about the final exam, but I'm thinking that maybe we can let you do a small project work. You can try to find out the hydrogeological data on the website, and then you can select a study area to put the hydrogeological borehole data, and then you can construct the 3D models, hydrogeological models by yourself, and try to take a look at the core sample or some of the image on the website. Try to do a comparison and provide some of the comments on the materials or classifications. And you can finish a work for the hydrogeological model. And seems we might not able to do the simulations because we do not able to get a license of the GMS for the teachings. So we are using the Python coding to provide like a GMPy to construct the models. So they will not based on the Hausen ID methods. There could be another like your subject point of view, how to draw the profiles like that. But it's still able to help you construct the model, hydrogeological model. And in the future, if we are able to connect to the FlowPy, they will be able to do the groundwater flow simulation. Yeah, but maybe this semester we are not able to do that work. So I think the target could be construct the hydrogeological model and try to writing a final report like that, based on the study area or based on the issues they would like to discuss. And you can use in the developed model to do some discussions. Okay, like that. Okay, and following we provide another topic is about earthquake hydrology issues. So that's the case study for the major earthquake events when we published the paper in Journal Hydrology. And in the past, we do a lot of earthquake hydrology investigations. And some of the researchers or in the beginning, because these issues is quite new, like it could be started from 1990s. So they could be quite new issue, and we try to start understanding the phenomena and behaviors. So in the past, there will be some definition or some of the concept is not totally correct. We try to propose some of the criteria to do the quantifications and meet the problems. So in this study, we try to change or try to find out what could be the inferences or what could be other factors to affect the phenomena or the groundwater response due to the earthquake events or due to earthquake triggering. And one of the important concepts that the sampling intervals in the groundwater observations, we need to set up the sampling intervals for the observations. Yeah, in the future classes, we'll also teaching how to do the settings and how to do the observation for that. So the sampling rate will largely affect your result. We know that the earthquake variations or dynamic is very quick. That could be 200 hertz, like this high frequency, 200 hertz or even higher. So if your sampling intervals is like 1 hour, traditional water resource agencies sampling interval is 1 hour. So you might not able to see the behaviors clearly. But in the past, we only have the hourly data to do the observations or to do the assessment. So we use hourly data to quantify the result. But when time passed, we found that there is larger differences. And what we define the oscillations might not totally correct. For example, this one, we see the oscillations, they look like just one peak and go back. And this is for the hourly data. And we might imagine, oh, there could be oscillation behaviors. But if you know that commonly the earthquake events, dynamic processes is only less than 1 minute, okay, commonly several seconds. You need to have a very huge earthquake events, and then you can persist for 1 minute. But for hourly, that means your data is already not dynamic behaviors. What you observed could be the residual or the after the change behaviors result. So even we see that they look like the step change or the oscillations, the original one may be much higher, and they have the change processes, so they decay the water pressure. And what you observe is just this time point. I forgot exactly which. Maybe if there's the okay, this is the main earthquake events. I forgot exactly the time. For example, the hour means that we just record in the 1 hours, 1 o'clock, 2 o'clock, 3 o'clock. So when your earthquake happens at the time, so that could be several minutes after, and you can have the first record. Okay, and that depends on the time that the earthquake occurred. So it's not uniformly. So that could be the processes already have the change behavior, and it's not easy to define the oscillation. And if we use in the secondary data, you might be able to see more clearly the oscillations behaviors. Okay, so that will be easy to see what the difference is between these two. And although the well is different, yeah, maybe I should use in the same well. We have the this kind of high sampling rate or sampling intervals observation. That's for the Central Weather Bureau at that time. They set up totally 6 wells in whole Taiwan area for the relative high frequencies. But honestly speaking, it's not dense enough to detect the signal. And for the mineral earthquake events, we see very unique conditions that the earthquake epicenter is far away from the damaged area. So we try to figure out what could be the main reasons to induce these kind of problems. And for the observation systems, we have the groundwater observation wells, and that's mainly for the Water Resource Agency. And that time still the 1 hour per sample. So we only have hourly data when we are able to see like step change quantities. And we also have the river discharge quantities. They will be able to provide you if their surface water have some anomalies. And when earthquake happens, commonly you can see the groundwater response, like we well known the liquefaction behaviors. But for the river part, the surface waters, they also have anomalies. And these anomalies mainly affected by some of the like groundwater system, okay, because they do not induce the additional water. They do not have the rainfall to increase the waters. So you need to, when you have the additional waters show up, that means you have the water release from the groundwater system. And for the earthquake events, commonly what we see, the river discharge quantities will be increased. Okay, we see the increased river discharge, and the quantity could be very huge. But that could be affected by several kinds of possibility, like you might have that reservoir dammed and then damaged, so they allow the water flow out, and that's not exactly the best flow increase. But some of the system is the increase from the natural system. They have the best flow increase, like they might have the fracture opening and induce the water release from the foothill mountains to the rivers. So you can see the river discharge increase. And that's proposed worldwide. A lot of the research talking about that. And in the Shih-Jung earthquake events, we see that quite largely. But in the mineral earthquake events, we do not see significantly. So we also check the river discharge quantity. Later you can see that. And in here we have the Water Resource Agency's observations. So we have the river discharge and groundwater wells. But we have another system, is the CWB, the Central Weather Bureaus. They are doing the high submarine groundwater observation. There will be only the 6 wells. Okay, so 2 wells is here, and there'll be others. 1 is here, and Ilan have 1, and Hualien have 1. Okay, so we have totally 6 wells to do the observation. Okay, and another part you can try to focus is that we have 2 plain area. We call this Pindong Plain, and this is Jiangnan Plain. And as I mentioned last time, Jiangnan Plain is mainly composed by the fine grained material, and the Pindong Plain is mainly for the gravels or the coarse sands. So the composition of the hydrogeology is largely differences, and that could be one of the reasons we can see later, so that response is largely differences. Okay, and the original earthquake epicenter is proposed here, but another professor proposed that there will be the sequence, earthquake sequence. First earthquake happens here, but the magnitude is not large, and the second earthquake relatively large, be triggered by the first earthquake. So this one will be the main earthquake events from their research. Okay, and the damage area could be around this area, and we have there will be the Xinhua Fault. This fault is very interesting part because that fault, around that fault we see a lot of liquefaction events. Not only the main earthquake events. In the previous we have the Jiaxing earthquake. This area also have the liquefaction occurred. And as I mentioned, that liquefactions occur is commonly due to some of the specific conditions. That could be you need to have the fine grained material like the fine sands, and you need to have the relative high water pressures or the high water pressure response. They are easy to increase the water pressure. And another could be they need to have the high enough the seismic energies to triggering. And some of the old concept could be liquefactions. After you have the liquefaction occurred, and the sand may become condensed. And when the sand become condensed, they might not easy to triggering another liquefactions. But that's not correct. Okay, from the historical observations, we can see that liquefaction occurred frequently. They can happen every time. Okay, you liquefy this time, but next earthquake occurred. Liquefaction occurred at the same location. Okay, so they can repeat to triggering the liquefactions, not only just one time and then become condensed. No, they can have the repeat phenomena. So in this area, Xinhua Fault, they have this kind of patterns. That's quite unique. Okay, and let's take a look at some of the results. This is what I say, the hydrogeological profile. This is for the Jiangnan Plain, and this is for the Pindong Plain. So let's take a look at the main material compositions. In the Jiangnan Plain, we can see that the color is the same. Okay, gravel is the blue colors, and coarse sands is the green colors. Okay, and the yellow color is the fine sand. Okay, fine sand, and then this kind of brown, relative brown color or orange colors is the clay and mud, clay, silt, and mud. Okay, and this is bedrock. This is another. Okay, so from this composition, you can see very clearly that in the Jiangnan Plain, we do not have the larger composition of the coarse material, especially the gravels, and most of the material will be the fine sand and the clay. Okay. So this kind of system, they become more confined system. And confined system, that means your existing water pressure might not easy to be dissipated. So when you have the earthquake triggerings, we said that the particle can redistribute it, and then the pore spaces be condensed and increase water pressure. And when your water pressure increase and continues to have the shakings, your water pressure continues to increase. And then you might reach the threshold of the liquefaction. Okay, when your water pressures equal to the total loadings, the total stress, and then your effective stress becomes 0, and then they become liquefactions. Okay, so this is the important phenomenon for that. So confined system is one of the importance contribution, and another could be they have a lot of fine sand and very shallow. Okay. When your fine sand is composite in the shallow depth, and your ground level, if they are relatively high, and this area, they will have the high liquefaction potential. If you calculate liquefaction potential index, you will got this kind of result. Yeah, I forgot to put the map for the liquefaction potential. Yeah, you can see clearly. Jialan Plain will be easier to have liquefaction. Okay, and Pindong Plain, there will be totally different. You can see that. The shallow depth is mainly for the coarse sand. And then we have gravels in the proximal fan area. And even they still have the fine sand, but the fine sand is relative. This one could be very shallow, because if they are very shallow, that means your ground table is lower than your fine sand. Then you will not have liquefaction. You need to have fully saturated conditions. So for example, if your ground table is around here, so above will not easy to have liquefactions, but below will have the possible to have the liquefaction. Okay. So that means you can see that this area mainly occupied by the coarse sand, and they are not easy to have the liquefaction. And another concept is that liquefaction commonly occurs within 20 to 30 meters depth. So around this depth, if your materials too depth, or if your depth is too deep, you will not have easy to have liquefaction, because your loading will be very strong. Your loading magnitude will be very huge, and then your liquefaction, you reach the liquefaction ability will be very difficult, because I mentioned they are balanced concept. Your total loading, you have the effective stress and port pressure. So your port pressure need to reach your overloadings, and then they can liquefy. But when you have very deep, your loading is too strong. So it's not easy to have the liquefaction concept. So commonly we say that there will be 20 meter or 30 meter depth, and very commonly used in 20 meters. And they also imply that when you have the basement, when you're building construct basement, if you have basement, you will not easy to reach the liquefaction limit, because you already removed the sediments there in the shallow depth. Okay, so the deeper they are not easy to have liquefactions. They become like your loading there. Okay, so we can imagine that this area is not easy to have liquefactions, and this area will easy to have liquefactions. And another is that when the system reach the liquefaction, or they go into the liquefaction processes, that means your ground level increase. Okay, so the same concept. This part, if you like to see the ground level increase or decrease, will be relatively difficult. And this part, after you excite the port pressures, and then you can easy to observe the port pressures persistent for a long time. We mentioned that when earthquake happens, to the record time, they have several minutes left. So if your dissipation speed is very quick, you will not be able to see the response for the hourly data. So this system, they will keep your port pressures more longer period of time, and then you will be easy to see the step ground level changes. And this one is the screen, so you can see that they have the shallow opening for the screen. And this one, although they have the shallow, but they are open mainly in the coarse sands, and this is fine sand. Okay, so we can imagine that for this kind of hydrogeological differences, they will play important role for the earthquake triggering ground level response. And for the water resource agencies well, so we try to do the statistic. We separate to 5 kind of the category. We try to quantify, we try to make the quantification or make the category to see the patterns, how large is ground level response. And when earthquake happens, the ground level can increase or decrease, depends on different kind of conditions. So we try to take a look at the statistic result. So we set up the threshold 5 centimeters to be 1. Within 5 centimeters, we define there will be no changes or not obviously. And from 5 to 30 centimeters, we define there will be slightly decrease or slight increase like that. Okay, and larger than 30 centimeters, we define as the larger decrease or larger increase. Okay, so this is the statistic we can take a look. in Jiangnan Plain, we can see there will be relative less, no response. But in the Pingtung Plain, we can see that most of the wells do not have the response. We only have 16 wells have the response, but only the slight increase. And for the Jiangnan Plain, we can see the slight increase is 45, and obvious increase is 31, the number, okay. And decrease also, slight decrease 9, and obvious decrease is 4. So we can see that Jiangnan Plain have more response to the earthquake, okay, groundwater system, but the Pingtung Plain do not have. So that's the first, you can imagine, you can see that from our hydrogeological point of view, we already expect this kind of result. So hydrogeologists affect largely for the groundwater response, okay. So this is the map. We'll try to see how the groundwater level responds. And the triangles point out to the uppers means the groundwater level increase, and point out to the lower means they are decrease, okay. And the dark color means they are obviously increase or decrease, and white color means slightly increase or decrease, and the circle, empty circle means they do not have the significant response. Okay, so we try to separate the different systems. And this is aquifer 1, aquifer 2. We can take a look at the differences. And we can see here have the more significant response for the groundwater level, and this one only have very slightly response. Only several wells have the response. And aquifer 2, the same. This one is this area is more obviously have the response, and the other do not have a significant response. And we can take a look that if this is the main earthquake same epicenters, let's still away. Although yeah, we do not have the observation well to do the proof, but we don't know. We cannot say if they have the obvious or not. Okay, but at least if the energy is dissipated radially, we can imagine that this area should have the similar response, or even here should have the similar response. Okay, because they are quite similar distance. Okay, but we can see this area have larger, but this area do not have. So this one illustrates that the hydrogeology play a very important role. Okay, they control very significant for this result. But another way is that we know that the response there could be two kinds of components. One of that is driving force, and the second will be the intrinsic properties. How we see the response is the result. Okay, so when the driving force is larger in this area, we can imagine this one will have larger response. And the driving force here is slightly, so we do not have significant response. In the data, we can also see that the PGA, PGV, the strong motions, acceleration and velocity will be strong here, but very less here. Okay, this is from observation. So look like the energy is strong here, but this one is not strong. Okay. And the second is, as I mentioned, the hydrogeology, they play the role. Hydrogeology, like this one, is confined system. So they might more sensitive to the groundwater level response. When this one is like more opening systems. So they are not easy to keep the response. Maybe they still have the response, but they dissipate very quickly. So we do not able to see the response quantity for hourly sampling interval. Okay, yeah, so it could be like that. And I want to say one of the points is that commonly we do the observation for the ground motions is on the surface, ground surface. So that means your wave need to propagate through the aquifer system, from the rock system to the aquifer system, and then be observed on the ground surface. So when we say that this area have the larger PGA, PGV, and this one have the less PGA, PGV, we imagine the energy is released in this direction. That could be possible. But another could be if they are uniformly distributed. But in this area, they are more easy to have the response, or they might easy to see the variation for the on the surface, and this one do not have. There could be another possibility. For example, they have more water, so they damp the energy, the wave, so that your energies become less. And this one energy becomes strong. Maybe that could be one of the possibility. Yeah, but commonly we do not consider that. We just say that there could be the intrinsic property response, but the energy, what we observe, the energy here is stronger, here is weak, so we do not see the response like that. Still have the azimuth directions. They still have the directions impact because they we do not able to define the fault for the mineral scrap because there's a blind fault. If we are able to define the fault system, maybe you can see the propagations for the fractal systems maybe in this direction. So the energy is released these directions. Okay, maybe. And the same in the aquifer 3 and aquifer 4, the response is quite similar. Although some of the places have the differences, like this area, they have the slightly uplift, okay, but the others do not have. And here I also put some of the colors here. The color means they have the equitar above. I mentioned that in the peneplain areas, most of the material is the coarse material, but we still have the clay distributed. But the clay is not uniform distributed. So some places have the clay, some places do not have the clay. So they look like this pattern. So the first aquifer, we do not have the clay above, but this area we have the clay above here and here. So the response of the ground level seems below the clay material, okay. But not always, but it look like they have this kind of pattern. And another interesting part is that we can see the obviously decline of the ground levels in this area. The decline events is not many, it's only 4 events. So this is 1 in the aquifer 2. And this one, the damage, the surface rupture. So we can also see that surface ruptures, we can see the surface rupture on the surface. And we can also see the ground level decline. So that means the fracture might induce the opening of the system and then ground level will decline. Okay, so this is the equitar system above, but this one do not have equitar. And we feel, what could be the reason why this one do not have equitar, but they have uplift ground level response? If there are many for the gravels material, what could be the reasons? Okay, and another could be, this 2 is also show the decline, obvious decline. Okay, so we see that Napa have obvious decline and Xinhua have obvious decline, and they are very close to the fault area. And this is Longchang locations. Also, in the equitar 3, they have the 3 decline, obviously, but they are along the fault, the Xinhua fault system. And this uplift, we try to take a look at the transmissivity. We know that transmissivity could be the ability to transmit or to let the water dissipate or flow in or flow out. So we found that the high, the dark red color means they have high T values. And this is relative light T values. So this area, they are located in the relative low T values. So as I mentioned, if the system or if your hydrogeological properties it's not easy to dissipate the port pressures, you might able to see more obviously the ground level response. Okay, so you also demonstrate that. And others could be like they might have the confine on the system, or if they are open system, commonly we do not see the ground level response in that area. Okay, so we try to understand what could be the reason they have the decline. So this one is one of the points in this study. And the mineral scrap may have been caused by the dislocation of the thrust fault within a shift, left shift component of a low angle dip with a depth about 10 kilometers and nearly east-west direction and a northwest dip. So this is the focal mechanism, okay, for the earthquake events. Although we have 2 kinds of the announcement. This one is from CWB, and this one is another broadband seismic network they provide, but they are similar. Okay. So from this, they are under the compression conditions. This one is compressions. This one is compression. So compression, this one is look like quite consistent. But this area, they look like have the compression, but we do not see significantly the increase. And this one is the instant behaviors, but we do not see clearly the decline, ground level decline behaviors. Okay, so they seems not able to use in the what we call dislocation model. That means we have the compressions to uplift and extension to decline water levels. So be careful because in the past research they commonly use in the dislocation model or column strain models to do the explanations. But this kind of system, you need to memorize that the fault system is quite deep, at least 10 kilometers. Okay, but what we see the ground observation, this one is several hundred meters. So there are larger differences, and we are not able to directly using the tectonic stress conditions to assess the shallow ground level response. Okay, so some of the researchers or some of the papers they propose the concept is not totally suitable for the widely use. Okay, so here's the compressions. We can see there's compressions in this area. So they seems like some of the result match. They have uplift, but this extension we do not see clearly any extensions or decline of the ground levels. What we see the decline is mainly still in this area. Okay, so they are not consistent for this kind of mechanism. And ground level changes versus distance. In the past research, they also try to define that. They're using a distance to define the ground level response, commonly using like a near field, intermediate field, and far field to do the definition. But for this case, we can see that they do not have significant patterns. Although away from epicenter or the fault ruptures, you might see the decline because the energy is decline. They will have that, but not always. Okay, in some of the specific conditions, like I mentioned that in the pinot plane is this color. So when you see the pinot plane, most of the ground level do not have any response. So they do not have any patterns like a larger decline behavior. No, okay. And this one the same if we using different epicenters 1 and 2 because they mentioned there could be 2 different epicenters. Okay, so they do not see clearly the pattern. But for Jiangnan Plain, it seems they still have the patterns like they have the decline. Okay, they have the decrease with the distance. Although they are not very uniform distributed, but it seems they have this kind of pattern, decreased patterns. They are energy dissipated, so still okay. But don't forget that the rock system and sediment system cannot be directly compared together. Some of the places they are in the rock systems, some of the places they are in the sediment system. So when you combine them together to explain, to using the stress and strain concept to do the explanations, it's not totally correct. Okay, and here's the 1 second sampling intervals result. Okay, we have this one is NAPA, is relatively close to the epicenters, and this is away to the epicenters. So in a very near field, we can see they have quite largely declined behaviors. But after a distance, this one is very close. NAPA is, Chishan is also very close. And Liujia is away from the epicenter. I forgot to put the location. Let me take a look if okay, here. We have location here, epicenter here, so Naba is very close, but Chishan is also not very far away, and Liujia is here. And Naba and Liujia, you can see they have a little shift step changes, but Chishan is only oscillations. They do not have these kind of patterns. But Zhuangwei still have this kind of decline patterns, the step changes. So they look like the ground level response phenomena is not totally correlated to your distance. Okay, they have other factors to induce this kind of variations. So some of the researchers using a distance to describing, like they have the step changes, sustained changes, or the oscillation changes, is not totally correct to match this kind of concept. They should be affected by energy, okay? And previous part is the ground level, some of the result, and later we're talking about the river discharge variation. Yeah, overall, river discharge is not directly connected to the hydrogeology, but they still have some implications, because as I mentioned that groundwater, surface water increase, they must come from groundwater system. There's no further water source to provide. Okay. So in this area, we have the Shih-Jung Wang. Okay. This one, we can see this before the earthquake event, and this dashed line is the earthquake events. And after the earthquake event, we have the totally dry condition. They gradually decline. When dry, this approach to zero. Okay, dry 8 hours, and then increase, uplift largely. So the decrease amount we can use in the, because this is a flow, river flow, we can use in the calculation to calculate the amount. Okay, so the decline is this amount, and increase is this amount. Okay. So that means they increase 800,000 cubic meters of the water. Okay, this part, this area, they increase quite largely if we using this to be the the baseline. Okay, so they increase quite much, but initially they decrease. Okay, they could be abnormal. And this well, this stations is here. We also see they have the increase around 400,000 cubic meters. Okay, so there's also quite large amount of the water released. And these two stations, they slightly increase. Okay, slightly increase. So we also calculate the amount. And most of the other do not have, and this one also have slightly. Okay, here, slightly increase, but also have decrease and then increase slightly. But they also after that they still have a decrease. Okay, so try to see when earthquake happens, what the variations occur. And commonly, as I mentioned in the literature, commonly we see the river discharge increase. Okay, so we try to discuss why they have the increase patterns. Okay, so we focus on the list several stations. They are in the same watershed system, and we try to remain. So this one, we have the significant increase. Okay, and these two do not have significant increase. These two do not have significant increase. Let's take a look at the result. Okay, these two. These two have slightly increased. We showed previously, and these two do not have the significant change. Okay. So that means in the same watershed system, the river gauge commonly just control like the watershed. Okay. So that means above that, they do not show any increase the river discharge. They do not have released the waters. And then in these two areas, we can see the increase slightly. And in this relative downstream, we can see largely increase. So that means they do not provide the waters above this area and provide slightly waters, and then provide a lot of waters around this area. Okay. Although do not have the very consistent result, but I forgot if I show that. Okay, I do not show that. This area have the liquefactions, some liquefaction around. So the river increase, river discharge increase is mainly contributed by the like kind of best flow increase. And foothill areas is commonly you can see that the groundwater level will have declined, but we do not have groundwater level in this area. But commonly foothill area, we can see the groundwater level decline. And that decline, the water will release to the downstream area. So that's one of the contributions from the best flow. And another could be the liquefactions. I don't know if you ever see the liquefaction phenomena or not. For the Tohoku earthquake events, they have the video on the website. I may not put. When the earthquake happens, the liquefaction occurred. The water be squeezed out very largely, so they could release a huge amount of waters during the earthquake events. Okay, so if you see some of the water increase, two contributions. One is the rivers from the best flow, and the second will be liquefactions. Okay, so in this area we have liquefaction events around. And another is the foothill area. Commonly we have the decline water level and release the surface waters here. And the other interesting issues that we see the vertical directions have the different groundwater level response. from the past that I mentioned that the researcher tried to define using the distance to describing the behavior or the phenomena. That means you do not consider in the 3D system, you only using the plane view to take a look at the result. But if you using a 3D system to take a look, you will find that different depths, in a very shallow depth, the 300 meters depth, different depths, you will see the different response. For example, these 4 cases. Napa whales is here. We have 3 different depths. This is the shallow depth, we can see the uplift. And this is the deepest depth, we can see the decline and then go back. And the second, the middle one, also the uplift and go back to the origin. Okay. So the pattern is different. 2 of that is increased, 1 of that is decreased. Okay. What could be the mechanism? The other Xinhua, the same. Although they have oscillation initially, but after that they uplift, and another, the deeper whales decline. Okay. And this one, shallow depth increase, deeper depth decrease. The same. Wujia, this is the shallow depth increase and deeper depth decrease. So interesting that these 2 have the similar patterns. They look like the patterns is like upward systems, because this is the water levels. Okay, water level means that we know that the high head to the low head. Okay, so that means your patterns is from the deeper to the shallows. Your flow patterns in the vertical direction, because the deeper is high head, shallow is the low head. So they have the pattern from the deeper to the shallows, and this is the same, deeper to the shallow. And the other is that they look like they approach to the levels, approach to the same levels. So they look like if you have the damage, aquifer damage, you might let the waters propagate vertically. So they might match or they might approach to the similarities. And the same, Xinhua is the same. They look like approach to the similarity, although they are not totally connected. But these 2 have the same patterns, that they have the downward flow patterns, but they are not exactly correct. We can imagine that when you excite the water pressures, the deeper part, if you have pressures, they will propagate to the shallows. But if you have the shallow high pressures, they will not propagate to the deeper, they just dissipate it, okay? So they don't need to propagate to the deepers. So these 2, you can see that they become a weight. They become apart, and this one become converge, and this one become diverge. So the pattern is different. Okay, so they are also controlled by the hydrogeological system. Okay, and what could be the mechanism to induce the increase and decrease? We try to using some further analysis. Yeah, but that's not easy to understand. So I might let it pass quickly. But for the other part is that we try to discussing why they have the significant decrease pattern. Because we imagine that if there are sedimentary materials, when the earthquake happens, the shaking abilities, phenomena, will then your particle redistributed, and then your pore spaces be condensed. We will see the uplift of quantum level or the water pressures. So expect most of the conditions uplift, but we see some of that is decline. So here show the we put the decline whales here. Naba, Xinhua, and Longchang, and the Wujia. These 4 whales is the decline. Obviously decline larger than 30 meters. And there will be slightly decline. Okay, so, slightly decline patterns like this. And this is the background is the geological map. Geological map is on the surface, so they still have the patterns to the deepers. Okay, they connect to the deeper. So the different depths, they might have a different result. And we can see that these 3 whales is approach to the Holocene materials, Pleistocene materials. Okay, that means they are. This is Togosan formations. So that means they are more rigid. And this area is mainly for the sediments. They are Holocene materials, so they are losing. So when earthquake happens, the losing material tends to be condensed, and your rigid material tends to be loose, to be broken. Okay, so this area they induce the damage of the rock. So we see clearly the drop of the water level response, and this Longchang is a little abnormal because it is not an approach to this area. But we found there will be another interesting issue is that this is a Tainan tableland. They have relative high elevations, or in the bottoms they might have some of the rock uplift. So that this area become the tableland. So that means they also look like the foothill area. Okay, although not so high, but they look like foothill area. So in this area, we also see the decline of the water levels. Okay. So that means that elevation or geology also play a role to induce the decline of the water level. And this one do not be discussed in the previous literature. Okay. And you can see that this several decline is also approach to this area. Only one. This one is this several is not very consistent, although they could be quite site dependent. Yeah, but most of the wells is located there. And here's if we take the profile, we take from the GSMMA as we mentioned previously. Okay, so we have the wells here. This is the Wujia 1. Here, Wujia, and this is Wujia 2. Okay, so this is Wujia 2. We see the decline. And this one is for the Naba 1, 2, 3. Okay, and Naba we can see that here 3. And the red colors, although this is the grain size material, grain size distributions, they look like the sediments. But from the GSMMA, they try to define the rock. They mark here's the rock. That means the above is the Holocene, and below is the Pleistocene. Okay. So that means this part is partially cemented or even cemented, could be partially cemented, and the upper part is uncemented. Okay. So it illustrates that in the deepest, you have the approach to the rock or the approach to the sedimentary cemented materials. So when the earthquake happens, it's easy to induce the damage and induce the decline of the water levels. Okay. So that's quite consistent. I want to address that hydrogeology or geology play an important role for the water level response. Okay, this is another for the decline. The previous part that we see is the hydrogeological system, confined or unconfined is the difference. Okay, we take 10 minutes break.